Hello people, today we're going to be talking about an important topic in BST or binary trees in general. Today we're going to be talking about finding the height of a binary tree using recursion methods. And before I go into that, I also want to talk about how you use recursion to do the depth first search, which is quite easy. So first of all, let's see that. So if you just want to do a depth first traversal, it's quite easy. Just use the method of NNR or LNR or LRN, and it's quite self-explanatory in a sense. Just this is N, this is L, this is R, and that's how the question works. I don't want to go deep into this part because I didn't find it that fascinating, and because it's at the end of the day, it's just printing whatever data we have, unless we don't point to the next or the right, so to the left or the right, or if it is a null pointer in that sense. But yeah, I don't find this fascinating. What I do find fascinating is finding the height of a tree. So let's put this side by side. I'll open a whiteboard so I can explain to you how finding the height of the tree using recursion binary trees works. Of course, first of all, before you want to learn this, of understanding what recursion is, how it works is very important. But even if you do understand recursion, there are two things I think you need to know about recursion. You don't need to know about recursion in depth. You don't need to know about it everything. Wait, how do I do this? How do I erase everything? Oh my God, yeah. Okay, so yeah, so you don't need to know everything about recursion. What I mean by that is not that you don't need to know recursion. What I mean by that is you need to understand the first you need to understand three best cases, maximum three, minimum two best cases of the recursion of the algorithm that you're trying to implement, and then you need to have the superficial view, because if you go to the recursion call stack or the recursion stack, that shit goes deep more you look at it. So that's why I don't really recommend going deep into recursion, but I do and recommend at least going into two, three levels. You can go as much as four, but like I cap it at three or four, depending on my depending on my comfort. So yeah, I hope you know what a binary tree is. So I'm gonna draw a binary. So I'm guessing the code must be somewhere in the left or right, or I'm gonna do whatever the fuck I'm gonna do in my edit. Anyways, so as I drew the binary tree just before this, let's say it's gonna be 30, and the next one's gonna be 25. This is gonna be 45, 40, 20, 28. We are not doing anything, but just assume it works, because I'm just trying to explain to you the concept, not really everything. So let's say 20 goes to 15, 16, this goes to just like that. So yeah, so let's say this is a binary tree, BST. Yeah, this is a BST because it's left and right. Left is less than the node, and left is less than the root or the parent, and the right is more than the parent. So yeah, that's the thing, right? Now let's see the code. What does the code say? The code says if the node or the R is whatever the fuck you want to name it as is a null pointer, then you return -1. By the way, this -1 can also be 0. It depends on whatever you want to name it as, because some people say the height is, for this, let's say, right, some people say the height is 1 2 1 2 3 4, but some people say 1 2 3, but actually the height is 3. So I think -1 is a more better way to approach this question. But at the end of the day, it's just an algorithm. It's just a number, so it's not a big thing. It's just a static number, so it's not a big thing anyways. Okay. Now we have an else case. The else case says int height. By the way, you can do this, but I think since I'm working in C++ and I don't much work with libraries, I did find something better than this online. The thing is, do a return and a math.max. You will see why this is important, and then just say height of tree, which is the whole function, and call it to left. This is the left part, and the height of tree, and that is the right part, and add it to b1, add it to 1. So this is max. You find the maximum of left and right subtrees and their height, and you add it to 1. Now let's see the algorithm. Sorry, let's see I don't know, it's not an algorithm, it's just, let's see a base case. Let's see what you need to understand. All right, so let's say you have we're starting from 30, right, because we are passing the root node. So it's going to be 30 here, and our code says 30 is not a null pointer, so we are not returning anything. We are going to left. First is left. We are going to the left part of it. Actually, you can also follow the L height R height if you're convenient, if you're comfortable with it. But this also works. But I am writing this code in terms of the L height and judging it in terms of the mathemax. But it's the same, anyways. So 30. The first thing we go to the right. So left. Is it a null pointer? No, because we have a valid something. We go to the left again. Term it as left here. Term it as left here. We go to 20. Is it still valid? We are still valid. We go to left again. Now we are going to 20. 20 is, sorry, we're going to 15, sorry, my bad. 15, is it still valid? Yep, it's still valid. Now we're again going to left. Now is left valid? No. 15, as you can see, does not point to anything. Neither does its right point to anything. So this left is finally going to null pointer. So we are getting a -1. So the left is going to give me a -1. -1, and we are going to the right now. We are going to the right part. The right part is also going to give me a negative. So the first case here is math max. I just assume it max, and -1 -1 -1. That's the maximum between these two numbers. We are adding +1, and we get 0. So this is gonna pass 0 here. We are gonna get 0. Now things get interesting here. So we get 0 from here, right? That means this length is 0. So we are going right. We see right, does 20 point to anything? Yes, it points to 16. 16, that's it. 16 also works in the same way that 15 works. So its max, so its height is also gonna be the same here. So it's gonna come 0. So 0 0 max 0 0 plus 1 equals to 1. So we are passing 1 here. Alright, we are passing 1. We pass 0 here, we pass 1 here. 25. 25 goes to 28. 28, same, it works in the same way. So we are gonna get something, we're gonna get its height to be 1. The same way everything worked in here. So 1 1. So max 1 1 plus 1 is going to be 2, right? We are passing 2 here. Now this, now what I'm trying to say is we have R here, right? Which is this whole thing. But let's just assume whatever this is, this works in the same regards that this thing has been working. So last step is max 2, whatever we get from here plus 1. And in this case, we are going to get anything less than 2. So it's going to be 2. This is going to be 2 plus 1. 3 is the height of the tree. 3. 1 2 3, that's 3, and height equals to 3 in this case. And I think we can take a picture. Let me just go up here. So the thing you need to understand in this code is just the fact that understand the base case, because like this, if you know, this is just a base case, like this is just a very simple basic 3 height. If you go deep and deep and deep, you can go to 10 height. Then you can see the call stack of, you can see the recursion stack go crazy, go bullshit. So yeah, I think that's the logic, and you should understand recursion, but not in a way that it really affects your brain. Just understand it enough. And this is the code. I think, I don't know why I'm showing it, but it's also on the screen right now. But yeah, and that's so yeah, let's do a quick revision of it. 30, we are going to the left. 25 is fine. 25 we are going to the left. 20 is fine. 20 we are going to the left. 15 is fine. 15 we are going to the left. It's not fine, so it's going to return -1. We are going to the right. Right is also going to return -1. Max of this is -1 plus 1 0. Left we get right, we get 0 0 comma 0 max 0 plus 1. Now it works like that. So the recursion always starts, the recursion for these kind of logic always starts from 0 or something like that, and then we go build our logic. So I hope you understand it. If you don't understand it, I don't think it should be, I don't think you should really scratch your brain, because you need to, if you understand this much, I think it's enough, because understanding the right part is also the same as understanding the left part. But even if you don't understand any of this, just know how we are structuring the recursion. And I think that's it.